events are independent. If you know they're independent, someone tells you they're independent, you have enough information that you could assume they're independent. And in that case, what you're saying is, if one event takes place, like someone having a manicure in a salon, the chance that they also have their hair colored at the same time, that probability of them having their hair colored at the same time doesn't change whether they had the manicure or not. That's what we're saying. Okay? That would be independence. And that's, in that case, we're just multiplying the probabilities to find the probability of both the manicure and the hair color. Why do I multiply? Well, that comes from this general property. The general rule is that to find the probability of two coincident events, you say, I'm going to take the probability that a person has a manicure, probability A, and of those times, given that A happens, in other words, the person has a manicure, what's the probability that B happens? Well, as I just mentioned before, we're going to, given the information that they are independent events, it means it doesn't matter if A happened, the chance of having the hair color stays the same. It's still 40%, like in the example that I gave. So I don't see it as blurred, so I'm not sure, Maylene, why you see blurred. So anyway, this would be the same as if you were to take B first, so the other event, and multiply it the probability of A given that B happened. So you could write it this way or that way, and magically, in general, these should be the same. Similarly, up here, in the specific case, I could do it by multiplying B by A, of course. Okay? So when I don't write anything, that's multiplication. Okay, so that looks like a lot of letters. Just always hang on to that example, okay? So the example being, if I was to have information on a large group, like here, enough information that I've observed 10,000 women, and among those 10,000 women, I see a pattern that reveals the probabilities. So it's really the long run. We're looking at the long run case. So in the long run, of those 10,000 women, if I was to observe all of them sitting on a park bench watching women enter and leave a salon, I expect to see, if these probabilities are accurate, 30% of them have a manicure and 40% of them have hair color. That means that 3,000 of them would have had a manicure, and of those 3,000, 40%, because the probability doesn't change, that given the information that they're independent, if the probability doesn't change, then I just say 40% of the 3,000 40% of the 3,000 is 1,200. I can also do it the other way. So of the 10,000, taking 40%, would be 4,000 women. Of this subgroup of 4,000 women, 30% of them should have a manicure as well. The 30% doesn't change. So 30% of 4,000 is again 1,200. Okay, so it doesn't matter which way I go. The probability stays the same if I consider one event or the other event. This is not necessarily the case in general. This is just if I told you they were independent or I had information that they were independent. In general, why would it be that a woman who had a manicure would be different than the others who had a hair color? Like, at any given time, the chance of having your hair colored is 40%. But should it change if you already had a manicure? Well, maybe if you have budget constraints, you don't have enough money, you don't want to spend more, or you don't have time. You have time constraint, you want to get going from the salon, you have other things to do. So in that case, the probability after having a manicure, the probability of having your hair color might change. In that case, they would not be independent. They would be dependent, okay? So I'm going to save that. You guys got to work through that. I have some other examples in the exercises that I'll show you. All right, so let's see where we left off. So the rules. So summarizing the rules. So the rule is, if two events are independent, then the probability of one event and the other event happening is the probability of the first event times the probability of the other event. And that's the independence rule. And as a summary to some of the rules you've seen so far, and it's good to remember things by grouping them together. Remember that if events are disjoint, you add their probabilities, right? And they don't overlap, then you just add their probabilities to find the probability of A or B. But if events are independent, that means they do overlap, and they have an overlapping piece called probability A and B. If they're independent, you would multiply the probabilities together. And I asked you to do this exercise. Review it in the videos online. That's on Moodle. You'll get that. Maybe I'll put that there. Yes. So whenever I want you to go to Moodle, I make a note for you to go to Moodle and watch the video. Okay, and that you can also go to my playlist of videos and find this page. And here we are, the sixth rule. The sixth rule says, if events are not disjoint, in other words, if they're overlapping, and remember that image of overlapping, so they're not disjoint. So if I wanted to know the probability of A or B, I would have to do something else. I would have to take the probability of A plus the probability of B, but then realizing this overlap was counted twice, so I need to take one off, and that's what that is. So that is the final rule. So there are 6 rules, keeping in mind the terminology for word problems, that finding the probability of A or B is a matter of finding the probability that either A or B happen. That's how you say it in English. And if you want to find the probability of not A or B, then you calculate using the complement rule, 1 minus probability A or B. And then in this case, we're saying neither A nor B happened. All right? Okay, so then I want to go through some distributions. Let's see. No, I'm not going to do that exercise. So I want you to work on these exercises. All right, let's do this one here. So I asked this question. I presented. So this is a way of looking at the probability distribution that I introduced last time I spoke to you. And this is a discrete distribution. That means I'm able to list all the possible outcomes. But this is distinct in that it's a joint distribution. It's joining two variables. One is class and the other one is gender. Okay? On this, so I have made like a matrix or a table of all the possible outcomes. The possible outcomes are to be interpreted as, this is the probability, so let me show you. So 0.12 is the probability of male and in occupation A. So those are occupational groups. It could be clerical, could be professional, could be medical, could be technical. However you want to imagine, there's different occupational groups. So the probability of being both male and in occupation A is 12%. That's how you read that. Okay, 12%. And the question is, are A and being female independent events? So what does that mean? Should they be independent? Well, what if they're not? It means that if I'm sitting and observing someone walk into the classroom, let's say, and I'm observing someone walk into the classroom and it happens to be a female. There are some occupations that are not traditionally female, like construction. Like, sure, there's some women who do construction work, but typically women don't do construction. So I have to be careful how I say this, right? But basically the point is, if you see a person walk in a room and it's a woman, your feeling or your sense of what occupational class they're going to fall into might change, right? Considering whatever I'm going to use as A, B, C, or D. So in that case, if that's how you feel, then occupation A and being female would not be independent events. They would be dependent, because once you see it's female, then the chance that it's a certain occupation might change. Overall, the probabilities would be different than in just the subgroup of females. All right, so let's see. How would I check this? How would I verify such a thing? Oh my goodness, I erased the whole thing. Okay, I just want to erase this. But how do I erase that? Okay, I'm going to erase this. Erase this. Very good. Okay, so how would I check such a thing? Just looking at the numbers. Okay, what do I need to do? What does independence mean? What's the rule? Well, rule number 5 tells us events are independent if the probability of A and B equals the probability of A times B. And it might not be the case, but if it is, they're independent. So I'm going to say and if this is true. So I'm going to use that. I'm going to check that. I'm going to verify that. How I'm going to verify that is I'm going to check on this side, which I'm going to refer to as the left-hand side. I'm going to compute this, and then I'm also going to compute this. I'm going to call that the right-hand side. So we're going to say left-hand side for this computation. And I'm going to call this the right-hand side for this computation. And we're going to see if they happen to be the same. So left-hand side, what is A and B? So which is the event, as I described before, A and B? A and B, for us, would be for the problem. Let me move it down so you can remember the problem. A and female. So woman would be this. So what's the chance of being a female? So that puts you along this row and A. That's this one here. So let me put it in words here. So being A, probability A, and being female, apologize for so messy. A and female. I ordered a stylus. We'll see if that helps. The probability of being A and female is that event there, 8%, because this one was A and female. So that's 8%. So I'm going to write that as 0.08. Is that okay? And now, what's the probability of being A and the probability of female? I need to multiply those. This indicates multiply. So let's see. A's probability, so let me write it down first. So this is going to be calculated as probability A times probability female. I should probably just write F. So then that's going to be A's probability is, let's move this down again. So A's probability is what? Oh, there's two events here. What should I do? What should I do? Let me see. I'm going to leave that for you. Why don't you try that for 2 minutes, and I'll check back with you. Okay, I don't see any answers, but let's see if I can help. All right, so A, to find the probability of A, would be a matter of, well, this is the probability of A and male, and this is the probability of A and female. Both of those together are disjoint because you're either one or the other, and that would make the probability, that would create the probability of A. So, because there only can be two things, one of these two genders. Okay, so this would be the sum. So I just sum these together, and that makes 20%. So that's 0.2 or 0.20. And I multiply by the probability of being female. What's the chance of being female? Chance of being female is the chance of being female in A or female in B, or you get the point. So what I need to do is sum all of these to find the probability of female. So these are called marginal probabilities. You can calculate the probability of being female from here, summing all of those, and that's going to be 28, 36, 37, 38, 39, 40, right? So this is going to be 40%. So that's what I put here, 0.40. So the answer, is the same. Now that didn't have to be the case, but it works out in this example that the probability of them happening, these events happening at the same time, occupation A and female, is the same as multiplying those two probabilities together. And this is a way, since these are the same, we say, since the left-hand side is equal to the right-hand side, A and female are independent events. So it's very specific understanding what is independent. It's a matter of thinking of being in the subset of one event happening. Okay. And in this case, it actually doesn't matter. So it's a particular occupation. So maybe, if you think of it this way, being somebody walks in the room and it's a female, your thought about what occupation they are, or this particular occupation, doesn't change. So that's probably something where the chance of being a man or a woman in the occupation is about 50% or so. So in that case, it could be management. Okay, so management kind of occupation. That would make sense. All right. There it is. So work with that. That's going to be the strategy you're going to take for answering questions like that. So what I want to do, I'm going to take the next half hour. I'm going to go over because I wasted the first 15 minutes. I'm going to spend the next half hour and I'm going to look at the different kinds of distributions for the rest of the course. I divide the kind of distributions you're going to see into two larger groups, the discrete distributions and the continuous distributions. The We begin with the discrete distributions, and I distinguish between two broader types. That's all we're going to focus on in this course. There are a ton, many discrete distributions, but I'm just talking about this course and the ones that need to concern you right now. Get good at these and they'll give you some insight in understanding other kinds of distributions. So let me read here. In particular, when we can represent the probability distribution of random variable x as a finite list of outcomes alongside their probabilities, x is known, so the big X, now we're going to say, that again, we use that repeatedly, but it depends how I define it and for you to be able to use it. X is known as a discrete random variable and it has a discrete distribution. There are the general discrete distributions. For example, I will give you a table like this. I will mention all the possible outcomes. Here they are, 1, 2, 3, and 4. These represent the month when an assembly arm will break down and the probability with it. So we interpret this as 5% of the robot arms will break down in the first month. Or in other words, there's a 5% chance that any given robot arm will break down. Okay, there's two ways. I'm saying the same thing when I say that, because I'm thinking of all the possibilities when I create a probability distribution. I see that because all the possible outcomes, their chances sum to 1. Within 2 months, there's a 25% chance that the robot arm will break down, and so on. In 3 months and 4 months, and you'll see. So within 4 months, so that's either the first, second, third, or fourth month, those sum to 100% because the robot arm should have broken down by the end of 4 months. I have presented that. Oh, geez, you guys didn't see that, did you? You should be watching and with your notes. Okay, so that's the presentation of the table. So it's showing the chance that a robot arm will break down in the first month is 5%. Or in other words, 5% of all the robot arms will break down in the first month. 25% will break down within the second, 50% within the third, and 20% within the fourth. For a total that by the end of 4 months, 100% of them will break down. Okay? I can represent this graphically with this graph. These are the heights of these represent these probabilities here, okay? I write probability that the variable x is equal to the value little x, and these are the possible values. There's nothing in between these spikes because the variable can only take on the discrete values through here. Okay, so that is the general discrete distribution. Where does that come from? It comes from observing behavior over a long period of time so that I can compute the long run relative frequencies. All right, so this is just observing the manufacturing process or the process of using the robot arms. Over a long period of time. Well, I could have done this for a year. I could have done this for several 4-month periods over many years to compute these estimates. Okay. All right. the next kind of discrete distribution, let me go back for a bit. Hold on a second. I want to go back just to say, what do I do with this? So with this information, I can ask you questions, right? So it's like the normal distribution. I give you the table, and then I ask you questions about variables that are normally distributed, and I give you the table of the standard normal distribution to help you make predictions. Well, here it is again. This is the probability distribution. I can ask you a question. What's the chance that the robot arm will survive more than 4 months? So let's see. What's the probability that X is greater than 4? So it means a very specific thing when I write that, right? I'm referring you to this table here where X is defined as the month that our robot arm will break down. The probability in this case will be 0 because it's not there. It won't exist. I could also ask you, what's the probability that the robot arm will break down in exactly 3 months? You would just pluck this out and write it down. It's 50% chance that it will break down in the 3rd month. And maybe I could ask you, what's the probability that it breaks down in the 1st or the 2nd month? I could say less than, let me fix that, less than or equal to 2. In that case, you have to add these two probabilities together for 30%. Okay, that's how we use this. So that is the general. In general, I'd have to give you that or give you information so you can construct it. Right? So you have to be able to construct that probability distribution, that table. Okay, let's go to the next one. So the other kind of discrete distribution is known as the binomial distribution. And we have a whole unit on binomial distribution that you can practice when we get there. I'm just going to do an introduction here, and then we're going to get more in detail actually exploiting the pattern that is very unique to this kind of discrete distribution. We're going to exploit the pattern, and I'm going to present a formula that's going to help you calculate probabilities, and which are used there as in the table form. It's actually programmed in Excel, this binomial distribution, and it comes in handy, and you'll understand that it's really binomial distribution is the basis of sampling and estimation, in fact. So it's a very important distribution. So here's an example. You saw this example where I define X as the number of tails in 4 flips of a coin. We actually derived the probability distribution at the beginning of this unit, and it looked like this. So if you don't remember, you have to go back and look at that, where I got these numbers from. I can depict graphically this distribution. There it is. Again, the values are here, and the probability is here. The probability that the variable takes on any of the distinct values. Either no tails in 4 flips, 1 tail in 4 flips, 2 tails, 3 or 4 tails in 4 flips. So we see a pattern here that we didn't see in the other distribution that we just discussed. There's a pattern here, and there's a symmetry here. That's the most important thing. Okay, now, are all binomial distributions symmetric? No, they're not. But there is a certain pattern to them, like I said, that we're going to learn how to exploit. So we need to know how to identify a binomial distribution in order to use the formula. And in order to identify it, I need to explain to you the 3 criteria for a binomial situation. So a binomial experiment or a binomial trial or set of trials should have the following characterization. It should be defined, that variable or that random event should be defined as the number of successes out of n independent trials. I often use this expression. You should have recognized it from the beginning of the notes. This shows all the possible outcomes from 0, don't forget it starts with 0, all the way to n trials. So the situation is that I'm going to repeatedly do something, and each time I repeat it or observe it, so I'm going to repeatedly observe or do something, and each time I observe, I'm looking for something in particular. And because I'm particularly interested in that one thing, if I don't see that one thing, I'm going to note it as well. So everything is relative to seeing the thing I'm looking for. I'm going to refer to the thing I'm looking for as a success. Okay, so either I'm observing married couples, and I'm going to say success is the chance that they're married in 5 years. They're still married in 5 years. So success is staying married. If I'm interested in divorces, I could define the success as, so success doesn't mean, it's not a value judgment, it's just what I'm looking for. So I might be looking for a divorce, and I'm going to see in the next 10 years, over the next 10 years, are they divorced or not? And I'm going to record if they're divorced or not. Divorce is a success. Okay? The instance that what I'm looking for doesn't happen is known to, that event would be a failure, or that outcome would be a failure. So this is the criteria number 1. Each observation has only one of 2 possibilities, success or failure. So I reduce the world into 2 possibilities. Reduce the possible outcomes into 2. The second criteria to be able to use the binomial formula is that I know the probability of that success. I know the probability of seeing what I'm looking for. Now that's a little bit bizarre if I'm going to run an experiment to find it, but bear with me. I'm going to introduce you to the theory, and then we're going to use the theory in instances where we don't have that information. Okay, so we're building the theory, and from there we're going to abstract. We're going to take out some of the things and estimate them. That's the idea. So the theory says I need to know the probability in order to compute, or in order to use the binomial formula. P is going to be the symbol used for the known probability of observing a success. In other words, it has to be given to you. And P, or I give you enough information you can calculate it. And P is the same for each of the n independent trials. So they're independent trials because P doesn't change. Okay, so it's kind of redundant saying that. So P is the same because the trials are independent, right? And the third criteria is that there are n independent trials. In other words, we know how many times we're going to look. I'm not going to say I'm going to observe couples for the next 10 years and not tell you how many couples I'm going to look at, because those would be the trials, not the years. It would be the number of couples I observe to see if they're married or not. Okay? So n refers to the number of observations I make. It's a finite number, so it can't be infinity. It has to be known in advance. All right? So if you have this information, that only one of 2 things happens, you know the probability of the thing you're looking for happening, and you're going to observe, you're going to look for that event a set number of times, and I'm going to call it n, little n. It turns out that p and n are all you need to know in addition to knowing that a variable is binomial. So these will be called the parameters, p and n, and with those parameters and knowing that you have a binomial random variable, you can compute the probability of seeing certain outcomes. So here's an example. At the beginning, I'm just going to make a point that this is how this should look familiar. You know, I'm going to express the probability, the random variable x as being distributed binomial, right? So B for binomial with parameters n, trials, and the probability p. And I write them as n comma p because that's alphabetical order, and I mentioned to you we like to put things in alphabetical order in statistics. Okay, so here's my example. Find the probability of seeing more than 5 people holding an umbrella on a rainy day if 100 different people are randomly selected and observed having an umbrella or not. So here's my experiment, or here's my set of trials. I'm going to try 100 times to look at people. And well, I'm going to look particularly at 100 people, let's say it more precisely. And so 100 is the small n. It's like my sample, right? It is my sample. And I know the probability of them holding an umbrella. I give you that information here, 10% chance. What's the chance that on a rainy day they're going to be holding an umbrella? Now, why would I want to do this? Well, let's say I'm working in a large mall and I was hired statistician, and they said that they needed to put out enough bags for umbrella bags, to avoid the floors getting wet. Okay, so we want to estimate from 100 people. So in other words, we're finding like the percentage of people who are going to have an umbrella on a rainy day. If I look at 100 different people, what can I expect? It's going to be 10% that have an umbrella. So from there, I can answer questions if I know the distribution. Is this a binomial? Well, let's review the criteria first. Is it true that only one of two things happens? Well, I'm interested in whether they have an umbrella, which is called a success, or not, which I'll call a failure. Do I know the probability of a success having an umbrella? I do. I was told it was 10%. And do we know the number of trials? Yes, I'm going to observe 100 people. Okay, so in that case, the parameters are 100 is my sample size, and the probability of a success is 10%. So x is distributed 100, 10%. And with that, since I know it's a binomial, I verify the criteria. I know it's a binomial. So I can, from there, using the formula that I didn't present here for you, but I will present it when we get to that unit. That's after we finish this one. You could calculate things like the probability that x is greater than 5. You can do this in Excel, or you can do this with the table values, or you can do this with the formula I'm going to teach you. The table of values you can find in many places online now. In the past, you'd have to have a book. You could purchase a book of tables, and that It would provide you with that information. What are the possible outcomes? The possible outcomes are no people would be holding an umbrella, one person, two, all the way to 100 people holding an umbrella. Okay, those are the possible outcomes. What's the probability that more than 5? The probability that more than 5 have an umbrella would equal, you could calculate probability x equals 6 plus probability x equals 7 plus all the way all the way to the probability x equals 100. So you'd have to have all those probabilities. Summing them together would give you the answer. Now I didn't present the table here, but that's the nature, that's the approach to solving this problem. Another way, well, we'll discuss another way to do that when we get there, but that's one way to do it. Another way is to think of the complement. Okay, and we'll talk about that later. Okay, so I give you an example. I also mentioned that there's other kinds of distributions, the Poisson and hypergeometric distribution. I don't end up testing these, but I put them here in case somebody's interested. They would fall in as discrete distributions that are very helpful, very useful. And I do mention them in the textbook. I reference them in the textbook, but this won't be on the final exam or anything. Okay. They also use the same parameters P and N, but they use them differently with different formulas. Okay, so here's an example for you to try. I'm going to ask you to try it, and I'll pick up and look at it tomorrow. So try this for tomorrow, all right? What you're going to do is read the exercise and answer the questions about whether this variable defined as the number of correct guesses in this setting, if that's a binomial distribution, and to identify the parameters. So that's basically what you got to do with the binomial, is at this point be able to identify if a variable is binomial or if it's just a general discrete variable. Okay, so try that exercise. So as I was saying, I started late, so I'm going to keep going a bit. So this is the second group. So there was just two groups of variables that we're going to talk about, the discrete and the continuous variables for this course. The continuous distributions that we're going to focus on are just three. There's just three types. So the first one, and I did discuss this in one of with some exercises in the review tests, understanding that density curves or density spaces should have total area 1 when the distribution is, when the variable is continuous. It's all the possibilities in between here. So you could have fractions in between here, or decimal values in between the limits of 0 and 16 in this special distribution. Now this special distribution is continuous. Okay? This is called the uniform distribution. I introduced it before. Formally it looks like this. X would be distributed uniform, with the lower and the upper, L for lower and U for upper bounds. It makes a rectangle, and what it means is that the chance of being of seeing an outcome, a low outcome, let's say, is about the same as seeing a higher outcome. Okay, so all outcomes are equally likely is a way to say it. You might hear it expressed. So if this was from 12, let's say this was from 12. Not very nicely written. Okay, so this would be from 0 to 4, and this is 12 to 6. The way that it's drawn, the chances of being in this space are the same as the chances of being in the same. That would be what uniform means. Okay, now why am I saying space, and what am I looking at areas? Well, because remember, this is a continuous distribution. Because it's continuous, we don't calculate probabilities at any particular value. We only talk about ranges of values, right? Okay, so since this whole area is 1, what must the height be? That's where we begin with this sort of distribution. Height must be such that the area is equal to the height times the width. Now area must be 1. So what is the height if the width in this case, how do you calculate the width? You will always calculate the width using the limits upper and lower of whatever space is of interest. In this case, I'm interested in the whole thing, right? From 16, the whole width. So the width is 16. Oh, why did I do that? I'm going to write 16. So since height times 16 is equal to 1, height must be 1 over 16. Does everybody see that? It has to be 1 over 16 for the area to be 1. You can see that algebraically, and you can also see that mathematically, that what number would I multiply by 16 to get 1? It has to be the inverse. It's 1 over 16. All right, since that is the height, now I can calculate different probabilities. I'm going to use this notation. What's the probability of being between 0 and 4? Well, it should be, again, height times width, but a different width, just the width here, and this width is 4. Right, so it's going to be 1/16 is the height, times 4, which is the width. So the answer is, the chance of being between here and here is 25%, or 1/4. It should also be the same here, right? Because that's 4 of width. The height has to be the same. That's the same. So the area will be the same. Okay, so I give you some exercise to try here. Why don't you guys try this one for the next class? We'll look at it together. So try this one and see if you can do it without me. There were some exercises on the review exams, so this should be easy for you, right? Well, the ones that tried, the people that tried. Okay, so the next two variables, types of distributions that are looked at in the continuous group are the normal, which you already know, so I'm not going to review it here. And then there's a special kind of symmetric distribution known as the t-distribution that I'm going to teach you in Unit 6. So that's it. I mean, that is it. Those are the kinds of distributions you're going to see. I'm not going to surprise you. Just get good at these ones, all right? And you should be fine. And what do we use them for again? Just to calculate probabilities. If I tell you a distribution, you should be able to estimate the chance of seeing certain outcomes. All right, so 2 I'm going to ask you to prepare for tomorrow, if you have the opportunity. I want you to try this problem. Try for tomorrow if you can prepare problem 1 and 2. The answers are here, but try not to look at the answers, or try and read them. Maybe I'll explain them better tomorrow. So you have 4 exercises I've given you to do. So try these 2. Prepare these. Prepare this one. And prepare this one. All right? So I will let you go. I'm sorry for all the technical difficulties. Not sure how to avoid that, but you guys are patient, I've seen, and I appreciate it. Let me know if you have any questions. In particular, what you should be doing right now is working through the probability notes, because you're going to have a quiz on Thursday, and I'm going to, let me confirm that that's true. I'm going to give you a probability quiz on Thursday. Yes. And I'm also going to open up the assignment that is worth 6% on Thursday. Okay, so start working through this. Work through these exercises on the practice. Work through the homework exercises as well. They're quite easy, the homework exercises. And then there's more quiz problems here with solutions. So you have all the answers here. Work through all of those. The only thing you should leave me for tomorrow is this conditional stuff. So I guess tomorrow I'm going to talk about conditional probability. And then Wednesday I'm going to work on this stuff, the rules, which is menacing, but you'll see it's not a big deal when I go through it. And then that's it, and you'll have Unit 4. So I think we're going to be in good time for Unit 4 quiz on Thursday, and then I guess I'll post on Friday. I'll start the next unit, the binomial unit. Okay, so I'm going to try and post every day for an hour. It works best for me, and whether you can get in on time or you can watch on your own later. Also, you can send me questions in advance, and I can fit them into the stream. Okay, have a good night, and keep on studying.